great pleasure to introduce Brett Windom. He's another one of our mechanical engineering energy faculty candidates. So Brett got all three of his degrees at University of Florida, most recent PhD in 2009. And then actually I missed this one, did a postdoc at NIST from 2000 to 2009, 2011. I was here in Boulder, right? And then after that, did here in Colorado.
Just making sure.
You really nailed this, Anthony.
I just don't want to get any of my facts wrong. And then I did a postdoc, so as part of Princeton University's Frontier Energy Research Center. They had a pretty unique postdoc where you did a year at Princeton, a year at USC. Is that correct?
USC and then Princeton.
Yeah. Close. And so that's a very prestigious postdoc. And then since 2013, has been on the faculty at University of Colorado at Colorado Springs, and where I've gotten to know Brett a little bit through the Combustion Institute and various things. So yeah, with that.
So I'm going to get into the core of this research, but the first thing I want to do is kind of just set up my research and my motivation and why I think what I'm doing on a daily basis is important. All right, so if we look at the United States energy supply in 2014, and it's going to be hard to see back there, I apologize. But we've got coal, natural gas, oil and gas, and biomass. And so those are all combustion energy conversion processes or sources. So it turns out 86% of our total energy comes from this chemical energy conversion process or from combustion. About 82% from the chemical energy conversion of fossil fuels. Okay. And so one of the questions I like to pose to my class when I teach energy-related subjects in thermodynamics is why? Why do we have so much energy dependency on combustion? And obviously economics and these things play a big role, but a more scientific answer is energy density. And to emphasize this in my classes, I like to show a couple examples. And so example one, I'm combusting octane with air. The heating value is 48 megajoules per kilogram of octane burned. So octane is a decent surrogate for gasoline. And we can do calculate the energy, the kinetic energy of my Subaru Forester traveling, yes, I'm from Colorado, I have a Subaru, traveling 60 miles an hour down the highway. It turns out the kinetic energy of my Forester traveling down the highway is equivalent to the amount of energy contained, yet completely combusted in 1 teaspoon of gasoline. So there's an incredible amount. Another example I like to show. So I was out filling my Subaru Forester up, and I had my stopwatch out, and I was measuring the time it took to fill up my tank. So I put in 13.7 gallons in 90 seconds. So I calculate a flow rate, and given this heating value of this gasoline, and calculate a power, and it turns out there's 20 megawatts of power flowing through my hand when I'm filling up my vehicle. And when I teach thermodynamics, it's a megawatt. What is a megawatt? Well, to put it in maybe some more common terms, a megawatt is the amount of 20 megawatts is the amount of power drawn by over 330,000. A ton of energy in this. So a lot of my research is related to the transportation sector, so I want to do a little bit of stats about this. So the transportation sector consumes about 27% of the United States energy in 2014. And if we look at what sources the transportation sector, it is 99.9% combustion, primarily the combustion of liquid fossil fuels and petroleum fossil fuels. Well, combustion of fossil fuels has its issues. We know our fossil fuels are finite. We will go out at least one day. Unfortunately, CO2 is an inevitable combustion byproduct. CO2 contributes to global warming, it's a greenhouse gas. We look at the transportation sector, we see that it puts out about 33% of the United States greenhouse gas emissions. And other pollutants are associated with combustion. NOx, SOx, soot, PM, aromatics, all have known health concerns. Well, if we look and see how well we're doing in the transportation sector, we see we're putting in 27 exajoules, that's 10 to the 18 joules, and we're outputting 5.7 exajoules of use of work. Based on my thermodynamics, that's an efficiency of 21%. So someone might look at this and say, why are we using these devices if they're our energy? Well, I look at this and say, there's a lot of room for it. So if we can increase efficiencies by 10%, it's not that much. 20%, not that much. Then that means 20% less fossil fuel, that means 20% less greenhouse gas emissions. So this is a critical near-term solution to ultimately becoming less dependent on fossil fuels and producing less greenhouse gases. So much so that the Department of Energy has commented on this. And why can't we? So what's limiting us? Why aren't we able to generate or to produce, to design these more efficient power plants? Well, based on a recent report, this quadrennial technology review by the DOE, it's a really comprehensive report, and it's a very interesting read. Their main reasoning is technical barriers preventing the development of these advanced power plants, these advanced engines, is the inadequate ability or inadequate understanding of the fundamentals of the in-cylinder processes that happen in our engines. And the inadequate capability to simulate them. We want to develop new engines. We want to be able to model. We want to use model-based approach to design these power plants. We need to really understand the physics that's going on. Well, it turns out driving a car or flying an airplane is far more complicated than you may have thought. We have highly turbulent conditions inside of our engines. If we didn't have turbulence in our engines, there's no way we could operate our engines at the speeds that we do when we want to. Well, if we want to resolve turbulence, then we need, on the complete description of the fluid dynamics, we need to resolve length scales from microns to meters. That's 6 orders of magnitude. Our engines operate at high pressures. We need to be able to know how pressure affects the chemical kinetics. This is not an easy task. Here's some data from out of Princeton from about 10 years or 5 years ago, showing experimental mass burning rates of hydrogen oxygen. It doesn't get any simpler than hydrogen oxygen in a combustion environment as a function of pressure and predictions by multiple different chemical mechanisms. So we see there's no agreement, especially as we get to higher pressures, 10 atm, 15 atm. So this is critical. Well, our fuels are not hydrogen and oxygen. They're made up of hundreds of compounds. Diesel fuel has hundreds, almost thousands of compounds. And if we want to be able to model the kinetics with high detail, then we need to account for thousands of species, tens of thousands of reactions. So this is tens of thousands of time-dependent reaction rate equation to solve simultaneously. And so here's just an example. This is a diesel mechanism. You can see the number of species and the number of reactions. And this mechanism was actually derived or developed based on surrogates. So it was only a 2-compound surrogate. Also, we have multi-phases. So our fuels, primarily liquid petroleum. And so we have to spray, we have to inject these fuels, and they have to change phase. So this means we need a very good understanding of the thermophysical properties and the phase change behaviors of these fuels at these extreme complicated conditions. So we're going to try to model this. We have to make assumptions, or else our simulation is going to take hundreds of years. So we have to make assumptions. And to make assumptions and simplifications to our models, we have to have validation terms and experiments, experimental validation terms, which means we need carefully designed experiments which are complicated enough to experience these conditions, but simple enough to be able to model. And so that's really where my research fits in. So I'm an experimentalist, primarily an experimentalist, with an emphasis on applied and fundamental technology. So when I look at my research experiences, I see it's kind of composed of these three main thrusts. So the first, fuels, understanding these thermophysical properties, specifically the phase change behaviors of these fuels. So let me talk a little bit about some of the stuff that I've been involved with here and have been involved. So as I said, our real fuels are very complex, hundreds of compounds, all with very different properties. So it becomes very difficult to characterize these fluids. So, especially the thermophysical properties. The thermophysical properties are important, for example, in this phase change. And so, I've got some ongoing work with a grad student at UCCS where we're measuring distillation curves, so boiling temperatures versus percentage of fluid distilled at various pressures. We're able to control the pressure. And using Clausius background equation, we can then predict the enthalpy of vaporization as a function of the fluid being distilled. So this is some work that we've submitted a proposal with some folks at NREL to apply to make these measurements with high ethanol concentrated gasoline tubes that are used in the direct inject application.
There's a word up there. What is moiety?
Moiety? So it's probably an organic chemistry word. So different organic structures. So aromatics versus a linear alkane versus a branched alkane. So the structure of the compound. Oh, and then we're also applying these type of measurements to assist in ongoing surrogate development research. One with Princeton, where they've been involved with developing surrogates for jet fuels, primarily chemical-based, so matching chemical properties of these fuels. We're now incorporating some of the thermophysical properties into these surrogate developments, as well as folks that I worked with as a postdoc in this. So I'm an experimentalist, so I've got to have tools that are able to quantify these environments. And so diagnostics is an interest and a common theme in my research. The reacting flows are highly transient and they have high spatial gradients. So we need to be able to resolve small length scales and fast time scales. And laser-based diagnostics afford the opportunity to do that. And some of the diagnostics that I'm involved with or have been involved with include imaging diagnostics, which can be semi-quantitative, including high-speed cliff, which I'll show you some results of once I get to the bulk of the research material or the topic of the title of the talk. Shadowgraph techniques, PIV. Here we use PIV to quantify the fluid dynamics in a high-pressure flame. This is some work that I did while I was postdoc at USC. We need to be able to quantify species and species production as a function of time. And so this spectroscopic techniques are important. These are more quantitative. Tunable diode laser absorption spectroscopy, Raman spectroscopy, laser breakdown spectroscopy are all techniques that I've used as a quantitative tool. Here's some research that I did while I was a postdoc at Princeton, where we were using TDLES, or tunable diode laser absorption spectroscopy, quantifying the production of species inside of a pulsed plasma. So we had our laser bouncing around through our plasma, and we could monitor the absorption and quantify that concentration of a particular species as a function of time. And this was used to develop plasma-assisted, plasma-enhanced combustion kinetic models. And then lastly, the reactivity. So this is really the fun part. This is where everything happens. The actual chemical conversion. And so when I look at this, I see One, just like understanding the thermophysical properties of these fuels at these complicated conditions, also understanding the chemical properties of these fuels. So making fundamental flame measurements, including ignition delays. How long does it take for the fuel in the air mixture to ignite at a given condition? Flame speeds. How fast does the flame propagate? Premix flame propagate. These are all properties of the fuel. Ignition, extinction behaviors. I've got a graduate student at UCCS right now who's we're working with NIST to measure extinction strain rates or extinction behaviors of jet fuels when they are used as coolants. So in a hypersonic application, they circulate your jet fuel as your coolant to cool your exterior surface or cool your engine. It's going to change the composition of your fuel. What effect does this have on key flame behaviors? We can then develop the appropriate kinetic model for these applications. All of these are important for kinetic model development. But they have to be done at these conditions. They have to be done at high pressures, and they have to be done under high Reynolds numbers or turbulence, so that we actually have true experimental validation targets that are computational or CFD model computational validating this. And then also related to this are some novel techniques. I already mentioned plasma enhanced combustion. I would tie this within this realm of my research interest. Another ignition engine phenomenon, so low temperature ignition, soot production, NOx production, wall effects, and how that affects the flame behaviors, and in-gas auto emissions. So when I look at my research program as a whole, there's a number of key funding sources that I have applied to and will continue to apply to. Number one is the Air Force. They're a huge player in combustion research, especially fundamental combustion research. So examples or types of projects I'll be submitting to them are these high Reynolds number, high pressure combustion, experimental combustion projects. This jet fuel surrogate work is being funded and is of interest to the Air Force. High pressure properties, so near critical, I had to remember, but near critical properties. This is really important in being able to, we can do our best at, we can do perfect at modeling the chemistry, but if we don't have a good idea of the actual properties of our fuel, the diffusion, the thermal diffusion, the connectivity with specific heat, all of these things, your combustion efforts are always endothermic fuels, these fuels used as coolants, and diagnostic equipment. So the Air Force has, or the DoD as a whole has funding opportunities to actually get equipment and these expensive tools to really do some of this work. So Duros, for example, the Department of Energy is another key player. So Basic Energy Sciences, the Vehicle Technologies Office. Already have interest by NREL in our thermophysical property measurements, our individual vaporization measurements for ethanol-containing fuels. This will continue to be explored, and other proposals related to engine combustion. And then NSF. NSF for their diagnostics, so MRI, to acquire the diagnostics I need, as well as the combustion platforms, rapid compression machines, high pressure combustion platforms in rapid machine. So these will be submitted through MRI grants, as well as big program grants. So career grant, I haven't submitted one yet. I was planning on submitting this summer, related to this multi-component fuel phase change behaviors and subsequent activities. Some smaller sources which are relevant to this research are ACS, Petroleum Research Fund, the Department of Commerce and NIST. I've had some success getting a NIST prep grant that I have right now at UCCS. And then other small businesses, and Colorado has a startup grants or proof of concept diagrams to your office so I can help with that. These will always okay, so that kind of sets up, that builds the foundation here. Now what I want to do is talk about and get into a little more detail about a research project that I've been doing with colleagues at Princeton since I was a postdoc there. So we just submitted our rebuttal, and I expect our second paper from this work to be published here next, will be accepted here next week. So the way I want to do this, I want to look at a jet engine. If we look at a jet engine, we can draw this cartoon. So we've got our hot air coming in, it's compressed, it's at high pressure, it's shearing, it's mixing with our fuel before entering this jet flame, or this main turbulent flame. And so the air coming in is compressed, it's high pressures, it's hot. So there is a possibility that we're getting reactions in this region prior to entering our flame. And if that's the case, then what's actually entering our flame isn't necessarily jet fuel and air, but jet fuel, air, and some partially oxidized species. And so this brings up a couple questions. One, how likely is it that we are undergoing reactions in this mixing region? Two, if we are, what effect does it have on the turbulent flame? And three, if we see an effect on the turbulent flame, what's the mechanism of response? So if we look at our fuels, so our jet fuels, they're very complicated, as I said, it's a chromatograph. Each peak represents a different species in our fuels. Multiple classes of moieties, high paraffin concentrations, as well as aromatics and other species. And they undergo some complex fuel chemistry, just like our diesel fuels do, as many of you have already familiar with. And so if I plot ignition delays here of our jet fuel, so these are experimental and some kinetic model predictions, as a function of temperature, so actually the x-axis we got 1,000 over T. But, so temperature is increasing as I go from right to left. I see that my ignition delays, or the time it takes for ignition to occur, decreases as I increase my initial temperature. Okay, makes sense. Until we get to around 900, 800, depending on the pressure, we get to these moderate temperature, and we see our ignition delays actually increase as we increase temperature, which is kind of counterintuitive than what we expect from our chemistry class when we talk about kinetics. So clearly there are reactions occurring at these moderate temperatures, 1000 K, 800 K. So this is called the native temperature coefficient. So what I'm going to do for the rest of this is I'm going to show experiments and calculations for N-heptane. So I'm going to use N-heptane as my jet fuel surrogate. So I can look a little closer at the ignition behavior of heptane. So here's a calculation. I throw my heptane in my air, stoichiometric proportions, I believe, 700 K, and I hit go. And I see, and I'm tracing the pressure or temperature. And what I see is two ignition events, ignition marked by a rapid change in either pressure or temperature. Okay. So I've got these, I got a first stage ignition where my pressure and my temperature rises slightly, and I've got a second stage ignition where I get my main heat release. This would be associated with a flame, for example. And so I can plot these ignition delays, again on this plot, 1000 over T, at a couple different pressures. So I can do the calculations at higher pressures and at lower. And what I see is the same sort of thing, starting off as I increase temperature, going from right to left. My ignition delays drop until I get to these moderate temperatures and I see the negative temperature. Well, I can plot my first stage ignition delays as well. Show me these dotted lines. And what I see is first stage ignition delay, especially at high pressures, is less than 1 millisecond. So that we're getting ignition events that are happening pretty fast with these fuels. Furthermore, I can do another little calculation where I can take, let's suppose we're highly turbulent and we're near a flame and we have recirculation. And so I have got an eddy that is circulating OH back into my flame preheat zone. So this is an OH radical, highly reactive radical. I can do a calculation where I basically dope my mixture with 100 ppm of OH. So not a whole lot of OH recirculating back and do the same calculations for n-heptane. This time it's at 20 atmospheres. It's a function of this 1 over T. And I see that my first stage ignition delays can now be less than, so they're on the order of 10 microseconds. So that's really fast. Right? And so we have highly turbulent conditions. And so there is a distinct possibility that we're getting recirculation from our flame into a preheat cycle, which could affect our turbulent flame machines. Our engines operate at high pressures. We see turbulence. We see our ignition timescales now on the order of return. So I think reactions, it's very likely that reactions are occurring in this mixing region prior to our reactants, based on these times. All right, so if they are occurring, well, what impact do they have? How does this change our composition? Well, I can plot the same simulation. Below it, I'm keeping track of my initial fuel concentration, or my heptane concentration, and also the production of some of these partially oxidized species, formaldehyde. So what I see is upon first stage ignition, I'm consuming over half of my heptane. So what's going into my flame following these first stage ignition events is very different than what I started with. So how does this affect the flame, the turbulent flame? That's the next question we're going to ask. How does this affect the turbulent flame? So we built something called the reactor-assisted turbulent slot burner, the RATS burner. Basically what it is, it's a reactor with a jet flame on the end. And it's long, so we can generate enough resonance time to induce these reactions. We can heat it up to 700 K and maintain high flow rates at up to 700 Kelvin prior to dumping our reactants into a turbulent jet. So we induce turbulence at a couple locations along the burner, and we characterize the turbulence intensities, our turbulent length scales, using hot wire as well. So we built this experimental set and tried to simulate this complex environment. And to characterize the flame that's coming out of our RATS burner, a reactor-assisted turbulent slot burner, we used laser diagnostics. So we performed simultaneous laser-induced fluorescence measurements of imaging the OH radical and also imaging formaldehyde. So formaldehyde was targeted because it's a key indicator of these low temperature emission events. And so basically in this approach, we generate a UV beam selected to excite both the formaldehyde and the OH species. We overlap those beams with 2 ICCD cameras on either side of our burner that are synced to collect emission from either formaldehyde or OH at the same instance of time. So here's an example of our OH fluorescence, where this boundary here represents our flame edge. So OH being generated at the flame going away from the flame. And at the same instance of time, in this window here, our formaldehyde, as you can see, is contained within our values. So we wanted to measure burning speeds, or turbulent burning velocity. So what we did was we took our OH cliff images, we processed them to find the individual flame perimeter, did this 500 times, laid all those individual perimeters on top of each other to find this kind of average flame brush. Found the maximum gradient in our flame brush to locate our flame edge. And where you locate that edge is up to you. To keep track of previous data, we use this maximum gradient point. And then using mass continuity, where U is our velocity coming out of our nozzle, which we have calibrated and been able to control. W is the width of our burner, length of the perimeter, the average perimeter length divided by the average perimeter length gives us our turbulent, or our average turbulent burning velocity. And so we can plot our average turbulent. So the first thing we did was we did methane. So we can plot our turbulent burning velocity normalized by the laminar burning velocity as a function of turbulent intensity normalized by this. And we do this normalization because it allows us to collapse data that is taken at very different equivalence ratios to a single correlation, as long as we're in the same equation. And what we see is our data for methane compares very well with previously reported data from co-production. So we validated our procedure, our technique. We're ready to do some high temperature heptane measurements. So we did a whole mess of measurements with reactor temperatures spanning from 450 to 700 K, velocities from 5 to 25 meters per second, equivalence ratios from ring to ridge. And if I look at the resonance times that we were able to achieve with these conditions, from 30 to 20 milliseconds, temperatures from 450 to 700 K. The region, our experimental region, is marked with this, this pink box. And so you can see we've got conditions where we have not achieved low temperature ignition, where we have achieved low temperature ignition, and even some conditions right around high temperature ignition. So that's something that we're currently exploring. I'll show you a little bit of data related to that. All right, so we did all these measurements, and what we saw was two distinctive turbulent burning velocities, depending on our reactor condition. So I'm going to characterize these two. So the first one here is that, so it's a slower flame speed. These occurred at lower temperatures or short residence times. So we didn't have our mixture exposed to this hot environment long enough to really induce these reactions. And so we see that we have slower flames, and I'm going to call this the chemically frozen regime. And then we had our cases where we had a reactor at high temperatures, long residence times, enough to induce a significant amount of low temperature reactions, and we saw our flame speeds accelerated. So as a result of these reactions occurring before the flame, we get accelerated flame speeds. And I'm going to call that the low temperature ignition regime. And so you can also look at the two images, and we can clearly see some very distinct behaviors in the emissions. So just to make sure that this is actually a result of these low temperature reactions, we did a set of experiments where we held our normalized turbulence intensity, U prime over SL, at equal to 3, and we increased the residence time that that mixture was exposed to this hot environment, so 650 K. And what we see is, as we do that, we are clearly transitioning from this chemically frozen regime to this low temperature ignition regime. And to make sure that it had to do with low temperature ignition, we monitored the formaldehyde. Well, formaldehyde is a strong indicator of these low temperature reactions. So we monitored the formaldehyde coming out of our burner using cliff measurements that we calibrated with GC sampling techniques. And we see that if we plot our formaldehyde concentration as a function of this residence time, the same conditions, the exact same trend. So this indicates that this result is in fact due to this low temperature ignition. All right, so as a result of low temperature chemistry, we've accelerated our turbulent burning velocities. So this leads to, it's just like research. You answer one question, it leads to 3 more. And so the next thing we wanted to do was understand why. Why is it happening? And so to do this, we wanted to know how is our fuel actually changing in our reactor. We wanted to get a better idea of what the composition is actually, what composition is actually going into the flame. And so if we could do that, then